So we came to the end of chapter 3 and we're going to outline the conclusions of this chapter. So what we have done in this chapter, we set the terminology and define the circuit theory. These are the Kirchhoff current law and voltage law equations. The independent of these equations, how we can find any number of independent equations from a given circuit is explained here, and this is a mathematical model. Now, what are the conclusions coming out of this chapter? Let's examine step by step. Resistive circuits, unique solution, linear equations. Linear, there's something wrong here. Linear, not properly written there. So we are saying now resistive circuits composed of dependent, independent sources and resistors can be analyzed, means find all the elements, current and voltages, by solving 2n times 2n dimension linear algebraic equations. So we are going to solve these equations. Solution of this equation is the analysis of this circuit. So conclusion tells us any circuit which is composed of independent sources and resistors. This is definition of resistive circuits. Has got a linear equation, algebraic equations as a mathematical model. So that means if the given circuit is a resistive circuit to be analyzed by us, then I know that the mathematical model is going to be linear algebraic equations. How I am going to write these equations? I am going to write 2n equations. Independent ones are going to be mesh Kirchhoff voltage law equations, and drop one of the nodes and write for the other nodes Kirchhoff current law equations and write the definition relations. All these equations, total number is 2n, unknowns 2n, then there is a unique solution. So these algebraic equations are the mathematical model, is the mathematical model of the given circuit. Second conclusion, analysis, elements, limits. So when we analyze a circuit, let me read it and then explain it. Current, voltage and power values are limited for components. So that means for a capacitor, for example, there is a voltage, the highest voltage that you could apply to that capacitor. If this voltage is over on the top of this limit, that means the definition relation is not true anymore. So if this voltage is over this limit, then the behavior of this element changes, or definition relation changes in mathematical sense. So we've got to have these elements lower than limits, lower than these limits. Another example, for a resistor, according to the manufacturer's informations about these resistors, that's the manufacturers, some of them says that the highest power that the resistor could absorb is 0.25 watts. Means if the power that absorbed by this resistor more than this 0.25 watts, then this resistor is not resistor anymore. That means chemically and physically it has changed. In other words, in practice, this resistor burned. So what happens is this. So the resistor value is not changed. Let's say 5 ohm resistor you've got, and the tolerant, the limit, power limit is 0.25 watts. So let's say before you go to lab, you're going to do the analysis on the paper by using pencil manually or by using MATLAB, whatever. So let's say you have chosen a resistor, 5 ohm resistor, and then you analyze the circuit, find this resistor's current and voltage, and find the power. If the power is more than 0.25 watts, means you are over the limit, because it says more than 0.25 watts power burns this resistor. So what you're going to do, you're going to go and look for a resistor which has a resistance value 5 ohms, but the limit is, let's say, 1 watt power limit. We're going to buy this resistor. This resistor expensive when the limit increases, so the price goes up. So this resistor value is different. This price is different. So we are going to buy this resistor in order to have that 5 ohm resistor running, not burning in our circuit. So why I explained all that, saying that the reason why we are calculating all the elements, current and voltages, because in order to understand whether a circuit does the job or not, we are going to check only the output signal. If it is voltage, you're going to calculate that voltage, and if the output is the current of an element, you're going to calculate that current. Once you see these output signals as you expected, that means your circuit is working. Why we are calculating the other elements, current and voltages? That is the answer. Once you find all the elements, current and voltages, then you can check the calculation results and the elements limits. You've got to keep your elements limits, you've got element limit value less than this. That means you're going to choose a right element limit available in the market. Example, you calculated and you found one of the resistor power 1 watts. You are not going to buy 0.25 watts power resistor. You're going to buy a 2 watts resistor and put it in your circuit. Otherwise, if you put 0.25 watts resistor there, it's going to burn. So this is the explanation why we are calculating all the elements, current and voltages. The last conclusion is the analysis, the minimal power. What minimal power, what is this? So let's go back to our circuit. That is our example circuit. Here, this is the power source, independent voltage source. In our houses, this is the power source. That means the energy comes from this source, or the power comes from this source. So this is our circuit. So to run this our circuit, we are getting power from that independent voltage source. Normally, what we want to have use minimal power and does the job. Let's say your electrical equipment you are buying. If the equipment power consumption is minimal, that is the ideal. The high electrical power uses electric equipment means you're going to pay for the electricity in order to run your equipment. So that means you are paying more. More you use it, since the power you're going to absorb by the circuit is high, you're going to pay that money to the electric company. It is not the price of your equipment. Conclusion. So if you've got the same electrical equipment, one of them consumes less power, the others high power. Of course, we're going to choose the one which consumes less power. Now, how I am going to calculate this, my equipment, electrical equipment, power consumption or absorption. So this power is going to come from the independent voltage source. I know the independent voltage source voltage. To find the power given by this independent source to the circuit, you've got to, we know the voltage of this element, and we're going to calculate this current, that blue current, that is I1. If I find the I1, so I know the power of this element. This power is going to be absorbed by this circuit. So this power then should be minimal. We are mentioning that power here. So if you look at these equations, the first equation here is in here I1 plus I2 here. I1 plus I2 equation there tells me I1 is the current that I am looking for, and I've got to know the I2. In order to find the I2, you've got to use the other equations here. Once you find the I2 from all these equations, you're going to say the negative of it is going to give you that I1. So that means the first equation here might seem that we don't need this. But since we need that I1, this equation should be included there. From that, once I calculated that I1, I know the voltage of this, multiplication of those two gives me the power. So if you see here, now go back here now, that current is, the result here is minus 2 amp. So multiplied minus 2 plus 20 here is going to be minus 40 watts. So this minus 40 watts means, since it is minus, that means this equipment delivers power to our circuit because of that minus. The amount of power delivered to this circuit is 40 watts. So in order to calculate this 40 watts, I need that I1. So we are saying the conclusion is, in order to find the power consumption of the equipment that we are using, we've got to do this analysis. That's another conclusion. So this is the final video that we're going to give you for the chapter 3. So if you consider the whole chapter 3 now, we start from the terminology, explain the theory, find the mathematical model, and set the conclusions. Sorry.